Hey guys, welcome back to my channel. How's it going? In this video, we're diving into permutations, a fundamental concept in combinations that helps us count the number of ways to arrange objects in specific order. We'll start by understanding the formula for permutations, explore its factorial-based form, and discuss cases where objects are indistinguishable. So what is the permutation? A permutation is an arrangement of objects in a specific sequence. The key idea here is that the order really matters. If we change the order of objects, we get a different permutation. For example, suppose we have three letters X, Y, and Z. So we have a set of letters X, Y, and Z. The possible ways to arrange them are X, Y, and Z, X, Z, and Y, Y, X, and Z, Y, Z, and X, Z, X, and Y, Z, Y, and X. So we have in total 6 possible arrangements. Let's now generalize this idea and derive a formula for this type of permutations. Suppose we have n distinct objects and we want to arrange r of them in a line. Well, in this case, we have a set of 3 letters X, Y, and Z, and we have the arrangements of 3 characters in a line. But in our more general example, we'll have a bit of different case. In case of n different objects, like object A1, A2 until the object AN, for the first object of each arrangement, we have n possible choices. So for the first object, we have n possible choices. If we take a look at our example with XYZ, we can see the first object, like this one, this one, this one, and this one, and this one, they all have 3 possible choices. It can be X, Y, or Z. For our second choice, we'll have n-1 possible choices. That said, the second element will have only 2 possible choices. It could be Y and Z, or Z and X, or X and Y, depending on which character was the first one, 2 possible choices. And for the third position, we would have n-1 possible choices. In our given example, it will be X, or Y, or Z. 1 possible choice left. So in this case of our example, we would have 3 times 2 times 1, which equals to 6. But what about general case? So in general case, we can actually proceed with the same logic. We can say that for the fourth position, we'll have n-3. And this process continues until we have placed our objects. Mathematically, this gives us the expression that the number of this type of arrangements will be equal to n times n-1 times n-2, and that way until n minus r plus 1. So we have placed our objects here. This formula ensures that each arrangement is counted uniquely. Sometimes this p can be denoted as p n taken r, or p n r, or sometimes p r n, like this. It depends on the text you're reading. In our case, we're going to use p on r, or we're going to use the p taken r, like this one. Now let's take a look at the factorial representation. We can express this using factorials, which makes this formula more compact. So p permutations n taken r will be equal to n factorial over n minus r factorial. What is the factorial? Factorial n can be defined as n times n-1, n-2, until the 1. And if you take a look at our previous derived formula, where p equals the n times n-1 times n-2 until the time n minus r plus 1, we can see that if we divide the factorial by the n minus r factorial, where n minus r factorial equals n minus r times n minus r minus 1, and so on until the 1, we can see that this expression nr, which is the permutations n taken r, essentially will be equal n times n-1, n-2, until the n minus r plus 1. So it will be the same. And if we apply this formula for our case, for our given example with XYZ, we can now see that permutations 3 given 3 equals 3 factorial over 3 minus 3 factorial, which equals 2, 1, and 3 here, over 0 factorial. 0 factorial in mathematics will always be 1. It equals 6 over 1. It is always 1, which equals to 6. So this is it. If we arrange all n objects with set that r equals n, and in this case, that will simplify the formula to p n taken n equals to n factorial over 0 factorial, which equals n factorial. This confirms that the number of ways to fully arrange n distinct objects is simply n factorial. Now let's take a look at 2 practical examples. Suppose we have 6 distinct letters, the letter P, Q, R, S, and T, and U. And we want to arrange 3 of them. So using our formula, that will be permutations taken 3, which will be equal to 6 factorial over 6 minus 3 factorial, which equals to 1, 2, 3, 4, 5, 6 over 1, 2, and 3. These values are reducible, and we have 4, 5, and 6, which equals 20 times 6, which equals 120. So that's our final result. There are 120 ways to arrange 3 letters out of 6 possible letters. Let's take a look at another concrete example. This will be about the permutations with repeated objects. What if some objects are indistinguishable? For example, let's say we want to count the number of distinct ways to arrange the letters in the word banana. This word consists of B, A, N, A, N, and A. So some letters are indistinguishable, they are repeated. In this case, we have 3 possible A's, we have 1 B, and we have 2 N's. Since identical letters are indistinguishable, we must divide out the repeated arrangements that do not change the sequence. That said, the formula for permutations with repeated objects is, so arrangements P of N, N1, N2, and so on until the NR equals the N factorial over N factorial and 1 factorial, and until the NR factorial. And applying this to our banana example, we have 6 letters in total over 3 possible A's, 1 possible B, and 2 possible N's, which will give us 720 over 6 times 2, 360, which equals to 1 and 60 here, which equals to 60. So there are 60 unique ways to arrange the letters in the word banana, because some of them are indistinguishable, and if we swap them, that will not make a new arrangement. Arrangement will stay the same. What it practically means, even if we interchange N with N itself, like these 2 words, our arrangement will stay the same. We'll still have the same arrangement like banana. They're indistinguishable. So this arrangement should not be counted. That's why we have only 60 possible arrangements with indistinguishable characters, because they do not change between each other. To grasp this concept in the most efficient way, you can think about these indistinguishable characters are separate groups. 3 A's will form one group, 1 B will form another group, and 2 N's will form the third group. It is the same group, and now each group has arrangements between each other. They have 3 times 2 times 1, 6 possible arrangements, which equals 3 factorial. That means we can interchange them between each other, like N, with another N, we can just interchange them, and it will not affect the result of our work. It will not affect the final arrangement, exactly as we just did for our banana case. The same applies for the B, but B is essentially just 1 character, so there are no actual interchanges here. And for the N's, we can have 2 factorial of possible arrangements, which equals to, so we can essentially just replace them between each other in 2 possible ways. For example, we can put N instead of N, and we can put this N instead of the first N. So there are 2 possible ways to arrange this. If we had 2 distinct letters, we would have A and B and B and A. But since we have only 1 letter, there is no need to count them as an arrangement. There is no need to count them as a separate arrangement. That's why we don't need to consider this number as well. Now, once we calculated the total number of arrangement, which equals to N factorial and equals to 6 factorial in our case, we just need to divide this by the multiplication of all possible arrangements here between these indistinguishable letters, which equals P and N1 and so on. 6 factorial, the total number, over 3 factorial, 2 factorial, and 1 factorial, which equals 60. So that's why we have this formula, because we essentially divide out our word by separate groups of indistinguishable characters, which have different arrangements between each other, which we do not have to count in our total result, which we do not have to include into our total result, because they don't actually form a distinct arrangement. So the key takeaways from this video is that a permutation is an ordered arrangement of objects. The formula for arranging our objects is essentially the n factorial over n minus r factorial. If we arrange all n objects, we get n factorial of total permutations. And when objects are indistinguishable, we divide them by factorials of repeated items. Permutations are a powerful tool in combinatorics, allowing us to count ordered arrangements efficiently. In the next video, we'll dive into combinations, where order will no longer matter. Thank you for watching this video. I hope you found this video helpful. And as always, if you have any questions, please feel free to leave them in the comment section below. I will always appreciate your feedback. And for more technical discussions, please join our Discord community. You'll find the link in the description section below. You can also connect with me in LinkedIn just to stay updated in future content and engaging into other discussions. And see you in the next episode. Goodbye.